Alright, good morning. I apologize that I'm not here. Our heater went out and I called the heating company. They came on Monday, they looked at it, and they said it's not the heater, it's the electrical stuff. And so called an electrician. Today's the only day they could come, and of course they had to come right in the middle of the day. So, we're gonna work through this. You guys are going to listen to me. Sorry, I'm not a fan of just talking through the whole entire lesson, but that's the way it's gonna be. Alright, so, I guess we'll just do the warm-up. I was gonna say, hey, let's pause and do it, but no. Alright, so we're gonna say a basketball player shoots 5 free throws. He's a 60% free throw shooter. We're going to assume shots are independent. X is the number of makes. And we're going to make our probability distribution table. So remember our formula to find the probability of X number of successes. So we're going to use that formula to fill in the probability for each of these. So like for 0, that would be the probability that X equals 0, so we make 0 shots. And that comes from 5 possibilities, choose 0 successes. Probability of success is 60%. So we have 0.6. We're raising that to the number of successes, which in this case is 0. And then we're going to multiply by the probability of failure, which would be 0.4. Raised to the number of failures, which in this case would be 5. And so we're going to put that into the calculator. Remember the combinatoric, you want to go to math, go over to prob. Older calculators, remember you have to type the 5 in before you choose NCR. We're going to have 5, choose 0, which there's only one way to have that. So this is 1. 0.6 to the 0 power is 1. So our answer is going to be 0.4 to the 5th, which gives us 0.01024. So then I'm going to do the same thing for X equaling 1. So I want to do my combinatoric 5, choose 1, 5 ways. Then I'm going to do 0.6 to the 1st power and 0.4 to the 4th. So 5 times 0.6 to the 1st times 0.4 to the 4th, which gives me 0.0. 7, 6, 8. Then I need to figure out 5, choose 2, which is 10. And then I'm going to have 0.6 to the 2nd power, 0.4 to the 3rd. Oops, I always forget that part. 4 to the 3rd. So we get 0.234. I said that wrong. 2304. Sorry. So now we're going to put 3. So we need 5, choose 3, which coincidentally is the same thing as 5, choose 2. We get 10. Then I'm going to have 0.6 to the 3rd, 0.4 to the 2nd. Get 0.3456. 3, 4, 5, 6, and I'm dropping pens because I thought that was such a cool number. 5 choose 4. It's going to be the same as 5 choose 1. So there's 5 ways that could happen. And then we're going to have 0.6 to the 4th times 0.4 to the 1st. So we get 0.2592. And then the last one, 5 choose 5, is going to be 1, just like 5 choose 0. And then we're going to have 0.6 to the 5th power, 0.4 to the 0. So that really is like 1. So we have 1 and 1. So really, we're just going to have 0.6 to the 5th for that last one, which is 0.07776. So now we have our probability distribution. And today we're going to learn how to find the mean and standard deviation of binomial random variables. And so the first thing we're going to do is we're going to take that probability distribution we just made and we're going to put it into our list. So we're going to do list 1 and list 2. So stat, we're going to edit, clear out list 1. Remember, hit clear when you're highlighting the list name. Enter, don't hit delete. So we have 0 through 5 free throws made. And then let's choose my probability. Alright, so hopefully you guys have your lists in there. If not, we can pause the video. But now what we're going to do is we're going to use our calculator to make a probability histogram of the probability distribution, which is why I had you guys put in your lists, because we're going to make a histogram now. So remember, once you have your lists in there, you want to quit out. We're going to go second y equals to get us to our stat plots. We're going to go in, make sure you turn it on. Type is the third one, which mine is already highlighted. X list is list 1, and then the frequency list is list 2. And then I'm going to hit graph. And I get no, well, you can kind of see there's probably a histogram over there. But, oh, nope, my y equals is empty. So I'm going to go back to my graph, and I'm going to hit zoom number 9. No, that didn't do me any good. Alright, well, if you hit zoom 9, that's what it gives you, and that's not a good histogram. So we're going to go into our window. Our x-min is 0, so I'm going to go to -1 just so I have a little space on the other side. Our x-max is 5, so I'm going to go to 6, and I'm going to go by 1s. The y is your probability, and I think our biggest probability was 0.3456. So let's make the minimum 0 and the maximum 0.5, and then we'll go by 0.1s. And I'm going to hesitate there. You can pause the video if you need to see the window. And there's our histogram. So we're going to sketch it, like we always do. So here's 0, 1, 2, 3, 4, 5, 6, even though I don't really need 6, but it works. And then we went to 0.5. So 0.1, 0.2, 0.3, 0.4. So this is 0. Excuse me. So from 0 to 1 is going to represent making 0 free throws, which the probability of that from the warm-up we know is 0.01024. So just barely going to get off the x-axis. And why don't we put the probability there, just to remind us. And then from 1 to 2, it's going to represent making 1 free throw, and that had a probability of 0.0768, so not quite all the way up to 0.1. 0.0768. From 2 to 3 will represent 2, and that had a probability of 0.2304. I almost said 234 again. So just a little over 0.2. 3 to 4, that's making 3, and that's the 3, 4, 5, 6, our biggest one. So almost halfway in between 3.3 and 0.4. 3, 4, 5, 6. From 4 to 5 will represent 4, and that was 0.2592. So a little higher than this bar. That was a really bad line, I apologize. And then the last one, 5 to 6, that'll represent making 5 free throws, and that was 0.07776. So that's just slightly higher than making 1 free throw. 0.07776. So we made our histogram. Now that I look at it like as a whole piece, it's kind of tilting to the left. Sorry, all my bars are tilting to the left. So this histogram that we made is called a probability distribution function. And of course, in math, we have a way to not have to write those 3 long words. So we call it a PDF. Probability distribution function, not like PDFs on the computer. And what a PDF does is it assigns a probability to each value of x. And we, of course, have a calculator function for it. And because we're working with binomial variables, our calculator is binomial PDF. And that'll tell us the probability for a certain x value. Same place as, sorry, I hesitated. Same place as normal CDF. So if we hit second bars, but you have to go way down in the list. But we'll get there in a minute. There it is. Number A. Number A, yes, I said that. Letter A. And newer calculators will prompt for the information at once. Older calculators won't. It wants N, the number of trials, P, the probability of success, and then X, the actual X value you're interested in. Now what we're going to do is we're going to make a table that shows the probability that X is less than or equal to 0, 1, 2, 3, 4, and 5. I don't know why I put dot dot because there's only 2 other numbers. That was pretty lazy of me. And then we're going to use the calculator to make a histogram. So first thing, we're going to make our table. So values of x and their probability. So we have 0, 1, 2, 3, 4, and 5. Now, if we did this right, when we get to 5, we should have a probability of 1, because the fact that we're doing less than or equal to tells us that we're taking the probability from the warm-up plus the previous probability. So like 0 stays the same, because there's no way to make less than 0 free throws, so the probability is still 0.01024. Then the probability of 1 is 0.0768, but I want to know the probability x is less than or equal to 1, so that could be 1 or 0, so I add those two together. So I'd have 0.01024 plus 0.0768, which gives us 0.08704. Then with 2, we're going to take this, because that's 1 and 2, and we're going to add it to 2. So I'm going to say plus 0.2304, which gives us 0.31744. Then we're going to add the 0.3456 of that. So probability of 3 or less is 0.66304. And we're going to add that, 0.2592, which is 0.92224. And then we're going to add that. 1, 2, 3. And we get 1. And then we're going to make a histogram. Well, I'm going to do it by hand, because we're going to sketch it anyways. And I just reminded you how to make a histogram on the calculator, so I don't need to do it now. So here's 0. This time our probabilities go up to 1. 5. 1, 2, 3, 4, 6, 7, 8, 9. 1, 2, 3, 4, 5, and 6. So again, between 0 and 1, it's going to represent making 0 free throws. I shouldn't say 1. 0 all the way up to 0.99999. Once we hit 1, then the bar represents making 1 free throw. So that one stayed the same, just barely off that x-axis. And then from 1 to 1.99999. So 0.08, so not quite up to 0.1. And then we make a big jump up to 0.31, so that's 2.3. So just above that. 0.31744. And then another big jump up to 6.6. This is 3.66304. And then 4. My bars are leaning again, aren't they? Ah! Try not to make your bars lean like mine. 92224. And then the last one goes up to 1. Alright, so that histogram, sorry about the Leaning Tower of Pisa. That histogram, yes, I laughed at my own joke, is called a cumulative distribution function, because cumulative, remember, means everything leading up to it. Cumulative cumulative. I'm going to abbreviate distribution, so otherwise I'm not going to pick. And again, we don't like to write long words in math, so we call it a CDF. Yes, like normal CDF that we've been using for months now. And remember, normal CDF, we would draw our normal curves, and it would be the whole shaded area leading up to that. CDF, because it's cumulative, everything leading up to our boundary point, or everything from our boundary point on. So it was cumulative, which is why we use normal CDF. So here, this CDF calculated the sum of the probabilities up to our highest x value, which for us was 5. So in other words, it calculates the probability of getting at most x successes in n trials. Calculator function here is binom, because we're working with binomial variables, CDF. Again, older calculators, you need to know that it's n, the number of trials, comma, p, your probability of success, and x, whatever x value you're interested in. Newer calculators will prompt you for that information. So here's the part where you guys would have been talking with me and you're just going to have to listen to me. So we're going to make a guess at the mean for the following binomial random variables. So first one, x is the number of heads out of 10 for a fair coin. So maybe make a mental guess to yourself. How many heads, if we tossed a coin 10 times, how many heads would we expect if we did a bunch of simulations of 10 flips of the coin? Hopefully, one of you is going, oh, I think it's 5. And the reason you think it's 5 is because a fair coin says that half the time we should get heads and half the time we should get tails. So our number of trials here was 10. Probability of success, 0.5. Then the middle one, the number of free throws made out of 10 by a 70% free throw shooter. They were to take multiple sets of 10 shots over a long amount of time. How many would we expect a 70% free throw shooter to make? Hopefully, somebody said 7, because 7 is 70% of 10. Again, 10 trials. Here the probability of success was 0.7. I forgot my equal sign with the doofus. There we go. So, in general, if x is the number of successes of n, where each trial has a probability of p successes, notice 10 times 0.5, 5. 10 times 0.7, 7. So really, to find our mean, we just naturally took n times p. So when we're working with binomial random variables, the mean is just found by taking the number of trials times the probability of success. Now, it'd be really cool if I had something like that where I could make you guess and just come up with a formula for standard deviation, but it doesn't work that simple. So I'm just going to tell you, standard deviation for binomial random variables is the square root of n times p times 1 minus p. Number of trials times the probability of success times the probability of failure, square rooted. So now we're going to look at using those formulas and using the calculator functions we just talked about. Next week when I see you, I will have Starburst, because I always bring Starburst for this, but I don't get to be here with you guys today. So I'll have it next week. So here's the situation. We have a bag of Starburst candies that can be considered an SRS of the whole population of Starburst candies. Since there are 4 flavors, the probability that each Starburst is cherry flavored is 1/4, or 0.25. Each bag of Starburst contains about 200 candies, so suppose we buy 1 bag of Starburst. X represents the number of cherry flavored Starburst candies in the bag. First question, let's make sure it's binomial, so we're going to check bins. B, binary. Do we have a success and a failure? We do. Success is getting a cherry flavored candy. Failure is non-cherry. By the way, my favorite's orange. I should have made orange a success, but I didn't think that far through. I made the whole female a success, male a failure. That one I thought through. So we have our success and failure categories, cherry and not cherry. I, independent. Here we can assume that it's going to be independent, because otherwise my whole example would be pointless, huh? But another reason is because of the SRS. Remember, that's a simple random sample, and that helps us to assume independence. We're actually going to get into excuse me, some other things to check to help us assume independence. So we're going to go with independent here. Then we're going to check N. Do we have a set number of trials? This one's kind of hidden. We only have 200 candies in a bag, so that's the most we can do for our trials. And then S, probability of success, probability we get a cherry, 0.25. So it is a binomial distribution. Down below, want to make sure you were paying attention to number 1. What is N? N is 200. What is P? P is 0.25. So then we're going to use our new knowledge to find the mean of X. So the mean of X, remember, is N times P. N is 200, P is 0.25. So our mean would be 1/4 of 200, or 50. So when we interpret, we would say something like, on average, we expect 50 candies to be cherry flavored in 1 bag. We expect 50 candies to be cherry in 1 bag of Starburst. My 2-year-old, he loves Starburst, but he doesn't call him Starburst. He says Starburr. Can I have a Starburr? Makes me laugh. Alright, what is the standard deviation of X? So I just told you that one. Square root of N times P times 1 minus P. Times 1 minus P. So number of trials, which is 200, times probability of success, which is 0.25, times probability of failure, 0.75, and then square root. Can't remember if I already said square root. So we're going to do 200 times 0.25 times 0.75. I'll have poopers. Get rid of that. And we get 37.5, so then we're going to square root that answer. and we get 6.124, I guess, if I round. 6.124. Interpret that. So remember, standard deviation tells you how far away from the mean you are on average. So the number of cherry candies, number of cherry in one bag will vary from the mean by 6.124 pieces on average. Number 5, what's the probability of getting exactly 60 cherry flavored Starburst? This word right here tells us that we're working with PDF, because remember, PDF, that was the first histogram, maybe if I can flip, and that assigns probability to each value of x. And we want to know exactly 60. So this question is asking us, what's the probability that x equals 60? And we find that by doing binomial PDF, and I am going to run out of space, of course. Let's see if I can make it fit. Nope, I can't. My handwriting's too big, sorry. So binomial PDF, first thing you need to put is the number of trials. Then you're going to put the probability of success and the x value you are interested in, which in this case is 60. So we're going to go to second bars, just like normal PDF, but we have to scroll way down to A, binomial PDF. Like I said, newer calculators prompt you, older ones don't. Remember, in the older one, put a comma in between the numbers. So we have 200 trials, probability of success 0.25, x value we're interested in is 60, and I get 0.017. So the probability that I have a bag with exactly 60 cherry Starbursts is about 1.7%. Question 6 is, what is the probability of getting at least 60? So at least is a inequality. So that tells me I'm going to be working with CDF. Now, CDF, if you remember, tells you the probability of getting at most x successes. So I'm at least is the opposite. At most is less than or equal to. At least is greater than or equal to. So when I do this one, I'm going to have to use our complement rule. Remember, we're going to subtract from 1, because CDF will tell me at most, the less than. So if I want to know greater than, I subtract from 1 to get the opposite. So what I'm going to do here, no way I'm going to fit it over there. So probability that x is greater than or equal to 60 is 1 minus the probability that x is less than or equal to 59. Notice equal to 60, so I had to drop down a number here. That is the biggest thing on this unit test that messes kids up. They remember that, oh, I have to subtract from 1, but they forget to drop down a number. If this is equal to 60, I can't use 60 here. So we're going to do 1 minus. This is a binomial CDF because it's less than or equal to. Again, number of trials, probability of success, and the X value you're interested in. Binomial CDF is right below binomial PDF. So we're going to go second bars, keep going down, and this one is B. 200 trials, probability of success, and we're interested in 59 because we have to drop down. So that's binomial CDF right there. But to find the probability X is greater than or equal to 60, I have to do 1 minus that answer. And I get 0.0625. 0.0625. So the probability I have a Starburst bag that has at least 60 cherry flavored ones in there is about 6.25%. Right. So now we're gonna flip over. Binomial distributions are important in statistics when we want to make inferences about the proportion P of successes in a population. So suppose 10% of CDs, well, this is old, you guys don't even do CDs anymore, but let's suppose 10% of CDs have defective copy protection schemes that can harm computers. A music distributor inspects an SRS of 10 CDs from a shipment of 10,000. Let X equal the number of defective CDs. What is the probability X equals 0? So the actual probability that there are no defective CDs in his SRS of 10 we have 10,000 CDs, okay? We're looking at a shipment of 10. 10% of those CDs are defective. 10% of 10,000 is 1,000. So 1,000, I can't speak, 1,000 defective CDs. Now, the music distributor is only looking at an SRS of 10. So what is the probability that in those 10 CDs, he doesn't get a defective CD? So we know 1,000 of them are defective, which means 9,000 are not. So the probability the first CD he picks is 9,000 out of 10,000. Then the probability for the next one not being defective, well, we picked a non-defective one, so there's one less. And there's one less total CDs. And we could go on, we'd have to do it for 10 of them. I'm not going to make you write it all out, but hopefully you guys believe me, the last one would be 8,991 out of 9,991. And we could find the probability that he didn't get a defective one. It comes out to about 0.3485. Now, I'm hoping you guys trust me on that. If you really want to, you could fill in the blanks in between. Using the binomial distribution, We're interested in exactly 10 not being defective. So, or excuse me, exactly 0 being defective. No defects. I said that backwards. Well, I said the same thing. 10 of them are not defective, so the probability of 0 defects. Sorry. So it's a equal to, so we're going to do PDF. We're looking at 10 CDs. Probability that it's defective is 0.1, and we want no defects. So we're interested in 0. So 10 trials, 0.1 for our probability, and we're interested in 0 of them. So we get 0.3487. Pretty similar to the actual probability. Only off by 0.0002. So the binomial distribution gives a good approximation as long as we don't sample more than 10%. The minute we start sampling more than 10% of the population, the binomial distribution is no longer a good approximator. So we have this condition that we need to start looking at. When you take an SRS to size n, little n, from a population of size capital N, we can use a binomial distribution as long as our sample, little n, is less than or equal to 1/10 of capital N, or the population. So really it's saying the sample is less than or equal to 10% of the population, which is what this statement set up here. We can't sample more than 10%. So building on that, as little n, our sample size, gets larger, something interesting happens to the shape of a binomial distribution. So the figures below show histograms of binomial distributions for different values of n and p. What do we notice as n gets bigger? So here, n is 10, p is 0.8. Here, n is 20, p is still 0.8. Here, n is 50, p is still 0.8. Notice that as n gets bigger, our distribution becomes more normal. So as your sample size increases, your distribution becomes more normal. And by normal, remember we mean bell-shaped, symmetric. So suppose that x has the binomial distribution with little n for the number of trials, and the success probability is p. When n is large, the distribution of x is approximately normal, with mean sub x being found by n times p, standard deviation sub x being found by the square root of n times p times 1 minus p. We already went through this. This is how it'll be written on your AP formula sheet. Okay, I didn't put the sub x before, but I gave you the same thing. As a rule of thumb, we can use normal approximation when n is so large that n times p is greater than or equal to 10, and n times 1 minus p is also greater than or equal to 10. These are the conditions that we check for normal approximation. So as long as we expect to have at least 10 successes and 10 failures, we can actually use normal CDF and normal PDF rather than the binom PDF and the binom CDF. So we're going to take that starburst example and we're going to show that we can use normal CDF and get approximately the same answer. So we have to, we're going to redo it with a normal distribution. To do this, we have to show these two things. So we check these conditions to make sure they're true. So I'm going to just kind of do that. N times P greater than or equal to 10. Well, that was the mean of the number of cherries, and it was 50. So we expected at least 50 cherry candies. That's definitely greater than 10. N times 1 minus P would be the number of non-cherry candies in the bag. So 200 times 0.75, which would be 150. Sorry, 10. I said 150. 150 is there. 150 is greater than or equal to 10. So those two things are met. So we can use a normal approximation. We know the mean is 50 for the number of cherries. From the previous page, we found the standard deviation was 6.124. And redoing problem 6, that was the probability that x is greater than or equal to 60. So we've got 50 in the middle here. That'd be 56.124. That's going to be like 62.248. And we're interested in 60 or bigger. So we'll say that's 60. And we're looking at that side. So we're going to do normal CDF, lower bound 60, upper bound big number, mean 50, standard deviation 6.124. And we get 0.05124. So if we go back and compare, we had 0.0625, 0.05124. They're pretty similar. Go ahead and try the exit task, and good luck on your homework, and I will see you next week.